So this week we are back to electronics. We first learned about coding and you simulated, then you designed electronics. Now we finally make circuit boards. And then from here, we're going to be off and running. Next week, we'll cover sensors. The week after that, all kinds of output devices. So this week, you need to be producing electronics and all the way through. So for inspiration to look at where we're headed, uh, Quentin, who I mentioned, who is a student turned instructor and is actually now in my lab, this is his assignment for the week, which was just a good version of all of the steps of making a circuit board, uh, soldering the components, and programming it and making it work. Then I linked Quentin was a TA for Isaac, and when Isaac did it, um, he wrote this great prayer to Quentin, which could apply to most of your instructors. Almighty Quentin, guardian of circuits, ruler of solder joints, we call upon your infinite wisdom to guide our shaky hands and steady our connections. When the components fail to align and the boards refuse to blink, we look to you, O Quentin, for salvation. Bestow upon us your grace and the power to debug. Let not our resistors smoke, not our traces burn. In your name we align our masks, we fix our solder bridges, and may the electrons bend to our will. Amen. So that could really be said to your instructors for this week, all of your instructors. Then for fun, Quentin, I see. That's I'll fix that link. Let me get to my notes. I'll fix that link. And this really belongs in large format machining, but I'm showing it in electronics production because this is a basic microcontroller board that Sean made that was 6 feet tall. And it works. So each of these giant components inside contains the little component, and so it's actually a working 6-foot circuit board. So that's background for what you're going to be doing. The main thing you're going to be doing is making the board you've designed. And at this point, you might want to do a redesign. Let's see. Stephen, Akash issue is he's using pages, and Julian will help you fix that. You probably want to redesign your board once we go through how you're going to produce it. But you're going to make the board and crucially test it. We want you to load code and run your board. At this point, we've done all the steps. So going back, and I don't want to nag, but Maria, Daniel, Midun, Jasmine, Bonmidi, Nicholas, Armando, if you're in class, your camera needs to be on. We need to see you as well as you see us. The body language is an important part of it. It doesn't work just to talk to names on tiles. So we are going to make circuit boards. How do we do that? A way we don't do it, but so you know the term dead bug is the term of art for this mess, where you just simply uh, put wires between your components. It's ugly, it's homely, it's occasionally done as a hack. You'll see the term, but it's completely unstable, unreliable. So that's called dead bug. It's not what we do. Etching is where you use a etchant to eat away at the material. And so this is a page on etching your circuit boards. The um, uh, issues with etching are you need, so what's good about etching is it's a batch process. It works in parallel over whatever area it is, and it works to very fine resolution. You can do it at uh, at integrated circuit resolution. Issues with etching, there's a setup. You have to expose or make a mask. And so you can do that optically. Um, this is about oh, one of the PCB tools talking about how you do that. You can do it with toner transfer as a process. You can do it with a printing process. Um, uh, then you need a chemical to eat away the copper. And ferric chloride, for example, is one of the typical ones. These are nasty chemicals. This is a page on using somewhat friendlier materials, from sort of supermarket, drugstore type materials. But when you etch, you're producing serious chemical waste. So any material you use has a safety data sheet that you need to, oh, it looks like somebody bought somebody in, I'll fix that link. uh, you're producing nasty chemical waste that you need to dispose of. And it's a really serious disservice if you pour it down the sink, you're etching your pipes and then you're polluting the environment. Um, making etching PCBs consumes a lot of water. If you have a meter square PCB, you consume a meter cube of water, and then you produce all of this tremendous chemical waste. So for all those reasons, we don't etch in labs. You can get set up. If you're going to do it, you need to work very carefully on the chemical disposal. Generally, we outsource that, although you need to be aware when you're outsourcing, you're generating tremendous chemical waste from the board houses. So it makes sense to etch when you're pushing the limits of the feature size and when you need to make many boards. But it's not an environmentally friendly process in-house. And there's also extra steps to do the lithography. We're going to use what are called direct write processes that directly produce output. So instead, we're going to be machining. This dates back to the Google Glass era, but this is a series of videos that show all the steps. And in particular, if we get here, this shows the key operation. Um, uh, Once you do all the steps, there's now a small high resolution milling machine with a tiny end mill, and then it's cutting away the copper. And what's great about this process is there's no setup. The design goes directly to the machine. And there's essentially no waste. There's just a little bit of dust you vacuum up. So it's a friendly process. It's a direct write process. It's not used industrially. One reason is I'll talk about the materials. The boards you can mill are different from the boards typically used commercially. And it's not a batch process, so you can't do many boards in parallel this way. But for Fab Academy, it's a much preferred process because uh, as soon as you have the design, you can be milling. In 10 or 15 minutes, you can be done milling, and you just vacuum up a little bit of easily disposed waste. So we're going to machine. Then um, sorry, I'm going to interrupt again. I don't know why it's a little bit worse this year. Rudolph, Kazutoshi, Yarun, Jogin, Thangam, Gonzalo, Sange, Maria. If you're in class, your camera needs to be on. Um, Class doesn't work when you're just tiles. So on the left is some boards I've made. And this week, there should be no variability. They should just always come out looking like this perfectly. On the right was a student assignment in the class, and I don't even know what went wrong. I can't even explain what went wrong in doing that. Um, but uh, don't accept anything less than what you see on the left this week. This week, they should just come out perfectly. Um, and some of the processes we do are very variable. This is completely consistent. There's really no variability. So there's a number of different uh, tools you can use for this process. So for many years, we've used these little roll-in milling machines. Um, uh, Behind me is one of these little tabletop milling machines. The spindle in that is upgraded. I'll talk about that in a little bit. But these used to be thousands of dollars. Now, for hundreds of dollars, you can get a little tabletop machine that works to very high resolution to be able to make the circuit boards. These are down, have come down far enough at the level that they're personally affordable. You could have your own. So little tabletop, but very high resolution milling machine. Then we're going to use tools. And so we had talked about end mills for machining. There's a smaller selection. So the very smallest one we use go down to 10 thousandths of an inch for tiny features. These are very delicate. They break very easily. So we only use those for the smallest features. This is a workhorse, a 1/64th inch end mill. Uh, that's one of the ones we use routinely. That's to cut out traces. It's not deep enough or strong enough to make holes or cut out the board. This is a bigger end mill we use that cuts out the boards and makes holes in it. You can use these V-bits. So the end mill was about $20. These are 10 V-bits for $12. These aren't end mills, so they're not perfectly clearing. It's just a flat surface that spins around. Uh, but these have gotten better, that the edges are sharper and the coatings are better. And so these don't do a good job of removing copper in large areas. They do a good job of isolating around the traces. And the strength and the weakness is the width of cut is determined by the depth of cut because it's a V-bit. And so if your board isn't flat, for example, the cut will vary, but that adjustability lets you pick very narrow cut sizes for fine features, for example. So these are a fine choice to isolate the traces, to go around the traces, but you wouldn't use these to remove copper in a large area. And then in between these, there's hybrids, which are instead of a long skinny bit, tapered bits. So the taper makes it stronger, but the fine tip goes down to a fine area. So this is like a V bit, uh, but it's sort of a hybrid between a V bit and a regular end mill. Um, uh, and let's see here. Let's see. Shaheen is sending an engraving bit, which is like a. I haven't used these, but it's like a small tapered bit. Okay. So you'll have these tooling in the lab. Uh, let's see, close that tab. Uh, and sorry, let me just double check my settings. Okay, that's all correct. So in your lab, you'll have a small precise end mill, and then you'll have these bits. So fixturing is going to be very important for this week because if there's even a little bowing in the board. Uh, you can break an end mill, and also the depth of cut will vary, and depending on the tool, the trace width can vary. So depending on your machine, one way to do it is just to use tape underneath the board to hold it down. If you have good clamps, and I'll show you some pictures of those, you can clamp the board from the side. Then underneath your board will be an underlay because we're going to cut through your board. And so you need an underlay you can cut into. One common problem is the underlays have a limited lifetime. As you mill, you're eating away at the underlay. Uh, and if you use the underlay, if it's been around too long, it no longer supports your board well. So it's important to change the underlay regularly as it gets used up. So a key parameter is going to be zeroing. So um, here's our copper, here's our tool coming in to machine. We're only going to cut a few thousandths of an inch deep because I'll go over the dimensions. The copper layer is very thin, so it only needs a few thousandths of an inch to cut through it. Anything more than that, you're wasting time machining. The issue then is zero for your end mill needs to be exactly at the top surface within a few thousandths of an inch. And so you need to zero the tool. And so there's a few ways to do that. One way to do it, and here I'm showing a bed with these T-nut slots and clamps for the fixturing here. One way to do it is just simply you bring your tool over to where you want to mill, you lower the tool, and you tighten it. That sounds obvious. The issue with this is it's very easy when you tighten it. The rotation of the tightening can lift your tool up a little bit. So to do that, it's a little deceptively subtle. You need to make sure you're holding the tool in position while you're tightening it so the tool doesn't move. Now, if it does, it's not a big deal. If it ends up a little bit up, what you can do is in software, you can just move the zero down a little bit. So that's one way to zero it. One way to zero it is if you hold a piece of paper and you jiggle it and you just in little steps move the head down, you start stepping this head down, and then when the paper doesn't move anymore, you stop, and then at that point you take it out, and then you lower the Z0 by the thickness of the piece of paper. And then a nice way you can do it in theory is it's automated. So many of these machines have a probe, and so they measure the conduction between here you'll see a plate there, and I've got that plate connected to my board, and here's the other part of the circuit. And when the circuit is closed, it exactly measures when you've Z0'd. So that automates the zeroing. The problem with that is if anything goes wrong in the process, you can break the end mill if the automated circuit isn't closing. So generally, what I do is I just lower the tool into position, but since there's always a little bit of walking, I lower it and then I step it down, a tenth of a millimeter or so, just to make sure I've zeroed it well. For this process, it doesn't hurt if you have it slightly too low. It's a problem if it's slightly too high. Your tool either is held by a set screw or a collet. And an important point for this week is that needs to be tight, but it's not like a weightlifting exercise. You don't use all of your muscle strength to make it as tight as you possibly can. That then over time will strip the threads. It's just tight to hold the tool. You don't fight against it with all of your force. So the end mill we're milling with, when you first start using it, it's very sharp, and actually the edge of the trace has very fine features because it's so sharp. The tool then gets slightly dull, and that slight curvature actually gives you a better finish. And but then towards the end of life, as the tool gets old, instead of cutting cleanly, it kind of smushes the copper. Now, there's a long period where it starts to look worse. So when the tool is happy, it comes out of the machine looking just like that. Towards the end of the life of the tool, the edges look bad, but they're not very bad. You can use light sandpaper or a file or even a straight edge, and you can deburr. You can get rid of the little machining features and clean it up. And then eventually you need to replace the tool. Um, so you machine, you deburr if there's any fine features on the traces. Then the next step is you clean the board. Oils from your finger on top of anything else, but just your finger oils over time will tarnish the board. And so after you machine it, then you wash the board, and then you're ready to attach the components, which I'll talk about. Um, tip Many of the things you do are going to be one-sided, but if you want to make a two-sided board, you machine one side and then you have to machine the other side, and you need to register those. This is a neat trick for doing it. It's slightly non-obvious. What he's doing here, so one way to register is you machine it. Here, let's draw that. Uh, you machine your board. This is the tool diameter. And then you flip it over, and what you do is you put your board in the, in the corner, and then the origin was here, and now you move the origin to there. So you use the frame to register it. Here, what they're doing is they're making this neat shape where you take the board out, you flip it over, and everything perfectly fits into the gaps left behind. And so that's a neat way to make a board that kind of auto registers when you flip it over into the same you don't have to change the coordinate system with that approach. So machining is the main process for this week. An alternate process is the vinyl cutter. So vinyl cutting PCBs has some skill, but some people fall in love with it. So when you vinyl cut, um, let's see, when you machine, the time is the machining area. When you vinyl cut, it's just the time it takes to move the tool that's much faster, but you then have to weed, which I'll talk about. But when you're done, you have traces you can put anywhere. So here he put it on this cube. He has good videos that show the vinyl cutting process. Um, and actually, yeah, I'll do one of his other videos. So so here we'll go through all the steps. Um, so we had talked about this in vinyl cutting week, but now it's for PCBs. So he has an underlay sheet that holds everything in place. The copper doesn't want to stick to its own backing, so he's transferring the copper to an epoxy film. You can also, I've used polycarbonate films for that. The vinyl cutting just takes a minute or so. Then comes the weeding process. And we saw that in vinyl cutting week. But here it really matters that if you cut too shallow or too deep, it won't weed cleanly. But when you've done that well, oh, that was came by too fast. You start shearing, not lifting, but you start pulling and you leave behind the traces. And then uh, with the vinyl cutting process, you can lay up as many. So there's one layer, but then what you can do is you can make via masks, and then you can make more layers, and so you can vinyl cut as many layers as you want. Um, you can use the vinyl cutter to make connections. This was somebody in the laser cutting week, but he used the vinyl cutter to make traces that he wrapped around the cardboard to make circuits. Now, after you've done the vinyl cutting, the traces aren't attached very strongly. So this is Victoria who fell in love with it. And what she's doing here is you go through all the steps of vinyl cutting, but the very last thing she does is an encapsulation. Uh, the vinyl cut board, the adhesive doesn't hold down nearly as strongly as the glue on the copper PCB. So what she does is she takes a clear epoxy and she just spreads a thin layer of the clear epoxy over the whole circuit, and that encapsulates it and anchors it. And that's particularly important for the connectors. Otherwise, the connectors can rip off the vinyl cut traces. And you can also do a hybrid. This was somebody um, milling, but instead of milling, uh, uh, she made her own stock. So she used the copper for the vinyl cutter and she laid it up, but then she milled that. And so she, in effect, made her own PCB stock. So you can vinyl cut. And unlike the milling, the vinyl cutting has skill. Some people hate it, but some people fall in love with it. So you could do all the electronics in the class just with the vinyl cutter. Then a fiber laser an ordinary laser cutter can't remove the traces, but a fiber laser can. A fiber laser is about 1 micron wavelength instead of 10 micron for CO2. This is about a $30,000 Trotec. One of the exciting tools for this week is the X-Tool F1 Ultra. This has two lasers, a diode laser and a fiber laser. And so, it's under $4,000. And it's galvo scanned, which lets you steer it very quickly. Now, the diode laser here, let's go back to there's a very strong wavelength dependence to the ability to absorb the laser radiation. And so for the X1 Ultra, let's see, there's a nice, so it has both a uh, diode laser source and a fiber laser source. And then they have their map of what materials work at what wavelength. But around a micron is typical for metal laser cutting. And the fiber laser sources are very efficient. They're used now in the highest power lasers. So a visible light diode doesn't do anything. Around 1 micron is the sweet spot for metal. And so with this, then this nice page goes through, and this is the key part of the process that when it's running, there's this bright green flash from the laser removing the copper, and then the color of the light changes when it gets to the underlay material. So what's nice about this is it's no longer limited by the tool diameter, it's limited by the beam diameter. It's very sensitive to the laser focus. In fact, I found generally in this process it helps to slightly defocus it. But when you have the setting right, it looks like this. However, it's misleading. Let's see, actually, I was just testing on it. Uh, it's misleading because when you remove the copper on the top, it can look like it's gone, but there's still some copper left. And so it looks like you've removed it, but there's some conductivity if you probe it with a multimeter. Um, but once you get used to what the underlay what the PCB stock looks like and what the color of the laser looks like, you can get calibrated. And so typically it might take 10 rather than one pass. It takes 10 passes of the laser. So it's not noticeably faster than machining. It's not slower. But the main attraction is the feature size can be much smaller than machining. It can simultaneously wipe out big areas and get into very tiny features. Um, then uh, this page shows after you've done that, you can also then apply a solder mask layer and have the laser remove the solder mask. And then finally, you can use the laser to cut out the outside of the board. And so you can make very finished looking boards with the laser process. That used to be much more expensive. That's come down now to thousands of dollars to do the laser scan PCBs. And one other neat thing you can do is this is a student in my how to make. Um, let's see, Shintaro is asking about aluminum or gold for copper. Let's see. Issue for gold is it's insanely expensive compared to copper. Copper is somewhat expensive. Gold is way more expensive. The problem with aluminum is aluminum grows aluminum oxide. Aluminum grows a tough oxide, and so you can't solder to aluminum. You can micro spot weld, but ordinary soldering doesn't work with aluminum. So that's why we use copper. LIG is a really interesting process. And so you can use the laser in Kapton to write graphene, which is a carbon material. The carbon is a conductor. It's not a great conductor. So you can use it to make sensors, and you can also use the laser to write laser-induced graphene, and then you can in turn plate the graphene as another way to make circuits with the laser. You can, so yeah, Ricardo, for the laser short, when you laser, you can get very fine shorts. The best way to do it, I find, is slightly defocus the laser so the beam's a little bit bigger, and you can run the laser in more than one direction, and that's the easy fix. So you scan in multiple directions, not just one direction. Garrett, the LIG is linked here on the class page. Um, so this was a student who did an experiment with using conducting ink, and so he made a mask and he printed with a conducting ink. This is a startup from a colleague that dispenses the conducting ink that works. They're not great circuit boards. Um, uh, so yeah, see, Akuri is asking again. I have gotten these were a whole bunch. I'll talk about these test patterns. I have gotten good results with it, but I found you really have to dial in the parameters that um, the number of passes, let's see, you want to cut fairly fast, and then you want to stop the number of passes just when you're getting through to it. And I was able to use, I actually got better results with the blue laser to cut out the outline of the board. So I'm still playing with the settings, but when you dial it in, I have gotten good results with the laser. Um, so it's possible to print plating. Yeah, yeah. Akiri, I'll post settings. I'm still tweaking my settings, but I'll post the settings for it. Electroplating is where you drive it's sort of like a battery. You drive a current in a bath that lets you plate circuits, and that's widely used, for example, for low-cost shoplifting tags, where you print with a poorly conducting ink and you electrically plate. And then this was an early page on sewing, uh, where you can use conducting thread in a sewing machine, not a very high resolution, of course, but you can sew low resolution fabric circuits that way. So those are all the different ways to make circuit boards. So then comes FR4 is the most common material in commercial circuit boards. So, it's different colors. Often it's green or uh, can be yellowish. That's epoxy with glass. We never machine that. One reason is glass doesn't deform for machining. It fights with your tool, so it's going to kill the tool. The other reason is short glass fibers. This is the same hazard as asbestos or similar to carbon fiber. It's hazardous waste. You don't want to breathe it. Fine particles in the air are a hazard. The waste you need to dispose of as hazardous waste. And so don't let FR4 anywhere near your milling machine. We use FR1. FR1 isn't used anymore commercially because it doesn't go to temperatures as high. In particular, non-lead solders need higher temperatures for reflow. But for manual soldering, it works just fine, and this machines beautifully. So FR1 is what we use. And FR1 looks very different. You don't, see, actually, uh, this shows it. So this is what FR1 looks like. If you look at it, you can see there's no glass reinforcement. It, it's a natural fiber in a resin. So that's what we machine. Garolite is essentially that without the copper. So you can buy Garolite sheets and make your own stock by laminating on it. Commercially, for flexible circuits, Kapton is used. Pyrolex is a flex adhesive. In the inventory, we have something different. This is an epoxy film, and then this is copper tape. And that's what you saw in that video from Hong Hao, using the vinyl cutter to make flex circuits. Copper is specified in, oh yeah, let's see. I'm going to talk about reflow shortly. Ricardo's putting in the link. If you try to heat FR1 from below, it burns. FR4 conducts heat. So you can fix that. I'll talk about hot air momentarily. Copper is specified by a weight per area. It's a funny unit. And so 1 ounce is typical. And that's just 35 microns. And so that's why we don't machine very deeply. Um, just, a few thousandths of an inch is deep enough to remove the copper. So this is how you make the boards. Then once you've designed your board, you can send it out to a board house for a commercial board. And so these our friends in Shenzhen have revolutionized it. So JLC PCB has a really easy to use site, quick turn, low cost. PCB Way is a little bit less convenient to use, but maybe a little bit more sophisticated, maybe slightly better boards, but they're pretty similar. And what those, among others, but those two have done is they've reduced the cost of the PCB production to dollars. You can get tens of boards for just a few dollars. Almost, unless you're in Shenzhen, almost all of the cost is shipping. But for me in Boston, an order from them might be $5 for the board, $20 for shipping, and it might take a week or so round trip. So they've just incredibly commoditized the PCB production. And so I don't use them while I'm developing and while I'm prototyping, but just like I happen to have here, this is a board that has lots of vias and fairly dense components and tight registration between two sides. And once I get that level of complexity, um, I send it out to a board house like that. And once I get up to maybe 10 or so boards, then I send it out. Um, yes, Enterprise, the fiber laser equally removes copper from the FR4 as well as the FR1. And in fact, it's a trade-off. I'm finding you can tune settings on FR1. FR4 is actually more robust against the fiber laser. SEM are uh, different standard bodies named. Those are similar. So the straightforward thing these groups do is they make your circuit board, but all of them also offer options where they can put the components on for you. And in one version, you send them the components, but this is so mature now, they have standard set of parts. And as long as you use parts they have, they can find parts for you. But uh, as long as you use parts from their inventory, they can assemble your circuit board. So for some of the components that are trickiest, smallest to attach, it can be convenient to have them do it for you. Let's see, I'm going to talk about Lumen, uh, and let me add, I'll get to Lumen shortly. So, um, design rules are key. A key design rule is how skinny can a trace be? And then another one is how close can they be? So a mil is a thousandth of an inch. 5 mil is typical for both trace width and trace spacing from a board house. In-house, a 1/64th N mil is 15 mils. And so that's a typical design rule. So we use fatter traces further apart to make them easy to machine. You can produce these if you're very careful with tiny tools, but typically we use uh, coarser spacing for in-house boards. Now, a one-sided board, this is one-sided. All the traces are on one side. Uh, I'm calling this a 1.5-sided board because I have a 0 ohm resistor. I just had one place where I had a trace that I couldn't route, and so I use a 0 ohm resistor to make the crossover. This is a two-sided board where I have traces on both sides, which requires flipping. This is here I'm using a milled board at the bottom, and then I'm using a vinyl cut board above it, and I could lay up multiple layers that way. Common at a board house is 4 layers, where you have top and bottom conductors, and then you have two internal layers that are power and ground. So that's available everywhere. That's more expensive. And then your computer or cell phone might have a 10-layer board to handle all of the routing. When you send the job out, there's your traces, there's a mechanical layer to cut it out, there's a drill layer for the holes, there's a solder mask for where the solder grows, and then there's a silk screen for the labeling. And those are all parts of what get produced for a board house. Then, if you look at this board, it has lots of tiny vias connecting top and bottom for the routing. If you just need one or two, like here, I just had to get from here to there. So I put in a via, but rather than flipping the board, I just soldered a wire for that one. Uh, in the inventory, we have these rivets. Here you drill the holes for the vias, and then you pop in these little rivets, and they make the connection between the top and bottom. Um, uh, in the board houses, they plate them. And so they use the electroplating process I mentioned to plate the vias. And in a complex board, a blind via is one that goes from the top to an internal layer, and a buried via is vias between internal layers. Those are much more expensive. Um, you can go from dollars to hundreds of dollars once you have a very complex board with all of that. Now, uh, you've seen me use Octopart for search engine. Through-hole components go into the board. We almost never use those other than a few special parts that need to be anchored. We almost always use surface mount parts. Um, Svavar, it looks beautiful in your background. Um, one of the benefits of having your camera in is we can see how lovely it looks in Iceland. Um, and then chip scale components are the very tiniest components that don't have leads, where you need to do reflow underneath, which I'll talk about. Now, what we're not using are breadboards. So breadboards are common for hobbyists. The, there are multiple problems with them. One issue is we don't make PCBs with components with leads that go in boards, but you need them for the breadboard. So you need a complete set of parts for your breadboard. Uh, the second is when you push wires in a breadboard, there's no documentation. And so if you come back a week later, you may not even know what's there. It doesn't help you make the transition to the PCB. Third one is they're actually have poor electrical properties if you care about noise or frequency. And then they have poor mechanical properties. If you take a breadboard and walk around, the wires can walk out and it can stop working and you don't know what's wrong. Instead, we're going to show you to make circuits as fast as you can breadboard them, but now they're made in a way that's documented, that's robust, reliable, and you can transfer from prototyping to production. So now you need to solder. Soldering is surprisingly subtle. In your lab, your instructor will come in with the soldering iron and the solder, and then take it away. And a beautiful joint, it takes 15 seconds, and you might spend hours trying to reproduce that. It's easy to miss. It looks simple, but it's surprisingly subtle. So soldering iron you use to solder. Typically, we use a solder station, and it lets you control the temperature of the iron, and it also has a hot air gun, which I'll talk about. When you solder, there's some fumes. Professionally, you need good ventilation. In the lab, we can use these simple vents that help pull it away. It's not really a hazard, it's more a nuisance. And then you need to be aware the iron is hot and you can get burned. It's almost everybody who's soldered at some point has like been looking one way and they reach with another hand and they grab the hot part of the iron. Um, it's a minor burn, but you obviously don't want to touch the hot point, but you need to be aware it can happen. ROHS is a European standard for reducing heavy metals, and it's pretty much taken over electronics. So if you have leaded solder in your lab, I would get rid of it and just work with lead-free solder that's friendlier for the environment. So here's a matrix. So there's wire and paste. There's leaded, lead-free, and low temp. So leaded solder solders at a somewhat lower temperature and is easier to use. Lead-free solder, you need a higher temperature, but you can learn to do it. And then for special processes, there are very low temp solders if you need to limit the temperature of the process. This is with a wire where you bring in the wire and solder. This is with paste. Um, we use paste for reflow, which I'll talk more about, but increasingly paste even for prototyping, is dispensing wire solder once you get used to it. So wire solder for each joint, you bring in the iron and the solder. With paste, you dispense the paste, and I'll talk about how you do that. Then you heat everything, and then the paste flows. And so paste lets you make components where you can't get underneath with the solder, but once you get used to it, it can be faster to reflow paste than to use wire solder. Um, and so, yeah, I'm going to get to solder masks shortly. So to solder, the first note is the tip of your soldering iron should be shiny. Um, the You should have a sponge, a wet sponge you use to clean the tip, and then you put some solder on the tip of your soldering iron. Then the key thing here is if you look at these joints, you'll see they're smooth and they're shiny. And that's the key skill for this week. So here's a component on our circuit board. Here's a lead. Uh, in the 15 seconds from the instructor that you might spend hours as a beginner. So here's the soldering iron. The first thing is you want to make sure there's a thin layer of solder on the surface. Your iron is clean and it's shiny. That thin layer of solder helps with the heat transfer. Then you bring the iron in here. You don't heat the lead, just the lead or just the board. You want to heat both of them. Then you can flow in just a little bit of solder, and the little bit of solder helps the heat transfer. It spreads out the heat transfer. But if you try to solder now, it won't work because the joint and the board haven't gotten hot. Then you gently probe with the solder and you're waiting to see when it flows. And that takes, you say, 10 or 15 seconds. When it's ready to flow, when you feed in the solder, it starts going up here and down there. And so if you try to do it too soon, you're forcing it and you get a bad joint. Then, crucially, once it's flowed, you wait a little bit longer. You keep the iron there for the heat to keep flowing and let the solder get into position. Then you take the iron away. And so when you're done, you then get a shiny, smooth joint. And that means it wet the uh, leads. So here are all the steps. So first, what I'm doing here is I need to hold the component to solder it. So I take a pad, I put a little bit of solder on the pad, and then I bring in my component, and now that little bit of solder is holding it. It's not a good joint. It's just I'm using it to hold it in place. Then I go to each joint in turn, bringing in the iron and the solder. Here I am heating it a little bit longer, and then here I have my shiny smooth joint. I go around to each joint in turn, and then I come back and I reflow the original joint, the one I used to tack it down. I just heat it again and I flow in a little bit of solder to make that's a good joint. So those are all of the steps of doing manual soldering. Now, a cold solder joint looks grainy. It's not smooth, it's lumpy, and it's grainy. And that's a common beginner mistake. Now, if you have a cold joint, you don't have to do it all over again. Typically, you can just come in, reheat the joint, and reflow the solder to clean it up. Um, Solder bridges is where you get solder between two legs on a chip or between pads. That's a common mistake. And so one of the first things you do when the board isn't working is just look at all the joints. Make sure there's no solder bridges. Make sure they're shiny and smooth. The solder in its core has flux. Flux helps clean and flow the joint. You can get a pen or flux paste. Some people swear by that to help solder. I tend to not use it. You can learn to not need it, but it can help. Now we get to reflow. So to reflow, you need a stencil. And this was during one of the boot camps. What we're doing here is this is polycarbonate, a particularly tough polymer. And then we're machining in the polycarbonate a stencil. Then what you do is you hold the stencil over your board, and then you can dispense the paste with a fine syringe, but it's hard to aim it at each pad. It's much faster to kind of smush the paste, and then you take, it could be a circuit board, and you just spread it out through the stencil. You lift the stencil, and magically every pad gets the right amount of paste. And that's how it's done in production. Then you need to heat it. So this is you can use a hot plate. This is a little tiny USB powered one. The problem with this is with FR1, it just burns. FR1 doesn't conduct the heat through, but it works perfectly fine to do it with hot air. So here what I'm doing is there's the paste, and noticed over here, I didn't even try to get the paste on each pad separately. I just made a thin bead. The paste wants to go where it's hot. So that I put all my components in place. And then here I'm coming in with the hot air gun. And then it's kind of magical. It starts heating, and then a moment appears where suddenly it goes from paste to silvery metal. And it looks very different when you do it this way, because instead of the solder going up the side of the pad, it's really underneath. And so you need to do that for the tiniest components that require reflow. But once you get used to it, many people fall in love with this process and don't use wire solder ever again. And you just dispense paste. And there's a little bit of an art to bring, if you bring in the hot air too fast, you can actually just blow the parts away. And so there's a little bit of art of bringing it in, letting everything heat up, and then watching the solder turn. But it's a technique you can learn to do it all with the reflow. And then depending on your eyesight, it can help to have a magnifying lens at the workbench to do all of that. So now we're going to stuff. Stuffing is attaching the components. You need to keep track of orientation. Every single person who's ever done this has attached a component in the wrong direction, like your chip is backwards. I'll show you how to fix that. And you should be, don't do the biggest components first. You want to do the smallest components in the middle, and then work your way to the outside. Otherwise, big components get in your way. So you'll make mistakes. So you need to desolder. So here's a version where these are really tiny leads. And rather than soldering each one separately, I made a mess. I had too much solder. And then I desoldered, and I'm left behind with everything done perfectly. So to desolder, you can use braid. This works great, but it has a trick, which is you have your, let's say here's your joint, that's the wrong joint. You bring in the braid, and if you just come in with your soldering iron, nothing happens. It's like a pump you need to prime. So you add a little ball of solder. The solder ball heats the braid, and then the braid wicks away the solder. But the trick is you have to prime the pump by adding a little solder to it. Then you can get solder tweezers. I don't use that. You can get solder vacuums. I don't use that. What I do use is gravity. And so what I'm doing here is, let's say this is the wrong chip, or I fried it, or I put it in backwards. I'm holding the chip I don't want. I'm coming in with the hot air, and I'm using the hot air to melt everything at the same time. And then at the um, at the right time, the board just drops away from me, and I'm left holding the bad part. And so with this trick of gravity, hot air, and tweezers, you can easily desolder and remove a part you don't want. Then you need to be aware that there's a lot you can do after the fact. So here's a board I made, and I made a mistake. I had the order of the pins wrong. So in here, I cut that trace, and then I tacked down a wire to go to the right destination. And you'll see commercial products shipping with fixes like that. So when you make a circuit board, if there's a problem with it, you're not done. There's quite a bit you can do by cutting and placing. These are tools that help you place tiny parts. This is a commercial pick and place. And then in the chat, there's a note. Lumen is a wonderful open source pick and place that's reduced it from tens of thousands to thousands of dollars. And in my lab, we've actually stopped using the commercial pick and place, and we just use this because it's friendlier and easier. And the page I showed you of the laser PCB is done by the person behind the Lumen. So these are great. There is a setup. We don't use this for one-off boards. The pick and place comes either when you're placing really difficult components or primarily when you want more than one board. Then it's worth the time to set up the pick and place. So we need to get our job produced. So Gerber is a bizarre ancient format. It's long past its due date, but it's what everybody uses. Um, I like PNGs. So I've complained about PNGs for compression. Here's where we use PNGs because PNGs have no compression artifact, that they're pixel perfect. So I like when you're making boards in-house, I like PNGs as a convenient format because it's easy to view it and it's easy to edit it. It's not standard for commercial production. For commercial production, you use almost universally Gerber. And so as a reminder, in Electronics Design Week for KiCad, I linked this. If you're using KiCad, this is a really handy tool. When you install this plugin, you get a button, and there's basically nothing to do. You just click that one button, and magically it produces all of the files you need for production. So for the in-house machining, FlatCam and PCB to G code are both tools that read in the PCB and make a toolpath for the milling machine. If you have Gerber, Quentin wrote this. This one is from Kerala. These let you take the PNG, take the Gerber and produce a PNG. Question about fusion. Yeah, generally the PCB cam is sufficiently specialized. I've never tried to do it with general purpose cam. Um, and again, I'll show you a few options. Industry just universally uses Gerber. There's so much entrenched everything around it. Commercial boards are Gerber. Um, uh, let's see. Shaheen, what do you, oh, you're talking about here further down?
Yeah, in the wiki, this video can maximize.
So this is something written in Kerala. Nice. Actually, that's doing the flip it over tabs.
Yeah.
Oh, that's great. You've automated that. Okay, then many years ago, I wrote mods, and I wrote it to make it easy to make workflows. This video is from an earlier version, but it's nothing has changed. So you read in the image, and then it does all of the operations to make the toolpath. And then there it is ready for machining. And then um, we'll read in now the exterior. And then this is a 3D toolpath to cut out the exterior um, and do that. And in fact, if you're fortunate enough to have a Carvera, uh, Carvera is about $5,000, but it's a really great tool because it's an automatic tool changer. So the steps with it, manually, you have to manually change the tool on like the little machine behind me, and then you have to re-zero it. The Carvera automates that. So this is a test pattern. In thousandths of an inch, I'm varying the width of a line and the space between lines. Here it is with the 1/64th inch end mill. And so you can see it can get down to there and then it can't get smaller. Here it is with the 10 mil end mill. And so I can get down to a smaller gap, but it's very delicate. Um, uh, then here it is with the V-bit. And you see the V-bit does a perfectly fine job. It can get down to a fairly fine gap. And it's about $1 per bit, and you can't break these. And so the V-bits really have gotten much better. And then here it is with the fiber laser. And so when you have the settings dialed in right, this is what it looks like when you get to the FR1 board without the copper. And you'll see the fiber laser is getting much further down to make much tinier gaps than you can do with the milling machine. And so that's the attraction of using the laser rather than the end mill. Then here's a key thing for this week. Here's a mistake I made on a test board. I was using my end mill, and you'll see I didn't I didn't resolve the pads, and then here I resolved it. Now this often requires changing the footprint. So uh, a standard footprint for PCB production may have a gap between the pads that your end mill doesn't fit in. But what we care about is the spacing between the pads. And so you can thin the pads so the end mill can fit between it, which might be slightly different than the standard pad you get. So uh, 50 mil is a standard pitch that's easy to do. 0.65 millimeter is pretty straightforward to do. Half a millimeter gets to be too difficult. But you need, when you make your PCB, if the end mill can't get in, before you decide you need a smaller end mill, you need to check the pitch of the pads to see if you can just thin the pads a little bit. And that's an example of that. Now, this is a video on debugging from Dua and team. You will make many boards that don't work. And so there's a standard checklist. First, check your joints, make sure they're shiny and smooth, no solder bridges, reflow them. Check the components are in the right orientation and you use the right component. Go back to the data sheet, make sure you're using the right pin. I showed you an example where I got that wrong. Make sure the connectors from the outside world are oriented right. then use a voltmeter to check the voltages in the circuit, make sure everybody's getting the right voltages. And after all of that, then we go to the test equipment and look at the signals in the board. And so you'll need to do all of that. You will absolutely make mistakes. So group assignment is run this test pattern. And if you're just using the most standard, V-bit on a tabletop milling machine, it should look like this. It should just be perfect. There should never be any variation in it. So make sure your workflow is working. Then as a group, I want you to submit a board to a design to a board house. It's up to you if you actually want to buy it, but I want you to go through all the steps to see how you upload the board and you price it. And it's up to you if you actually want to turn around and order it, but I want you to see that. Then I want you to make and test a microcontroller board you've designed. And crucially, you're going to mill the board, you're going to solder the components, you're going to run the program you've written and check that it works. And so for this week, for the time management, you need to leave time for doing all of these steps and them not working, and then you need to figure out what's wrong. So give yourself a day or so to update your design based on the design rules. Say a day to learn to make boards, a day to make the board, a day to solder, a day to load code, and then you need the remaining time to debug. And then extra credit is try more than one process. Start with machining because that's so simple, predictable, and useful. Then you can try vinyl cutting. If you have access, you can try laser milling. I'll update notes from my settings for the fiber laser process. And at the end of this, you should have working electronics. Then you need all of this mastered because the next 2 weeks are going to be sensors and actuators. And so to get through those weeks, you need to get through this week and be comfortable making circuit boards. Okay. As usual, Saturday team to help you with anything under the sun. No recitation this week. And there isn't a special, well, it's not an unusually creative week. It's just making the circuits, but it is interesting trying the different processes, and hopefully there's creativity in the boards you've designed. So happy PCB making, and I look forward to seeing your working electronics next week. Bye-bye.
Bye.
Bye, thanks.
Chala, Virit.
Bye bye.
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 Bye. Adiós.